All right. Hi, everyone. Like Sam said, Wells, and I'll be teaching you about reverse engineering on iOS. So who am I? Well, I'm currently a student at the University of Waterloo, working on my bachelor's of software engineering, and I graduate in under a year. In the past, I've interned at companies such as Facebook, Square, and Lookout. Well, I've been into softboarding since I was about 12. I started learning about reverse engineering when I was 19, and I was reversing malware and doing CTFs when I was 20. So why worry about mobile, or more specifically, iOS reverse engineering? Well, today, mobile is a very popular medium, and as a result, more information is stored on mobile devices, so their security is important. We know mobile malware exists and is a serious threat, even on iOS. So reverse engineering mobile apps helps with this. My goals today are to an array of iOS reverse engineering tools and give you the skills to get started on reverse engineering iOS apps. I also hope this talk inspires you to learn more about the tools on your own. The overview of what I'll talk about today is first, I'll give a brief introduction to reversing, including the compilation process and disassembly algorithms. Then I'll talk about the iOS architecture. The tools I discussed are Wireshark, Clutch, Dump Decrypted, Strings, NM, OTool, ClassDump, IDAPro, GDB, and Cycript. I'll go through the tools in the order in which I would use them if I were reverse engineering an app. I will demo many of the tools using a version of a popular game, which I obtained from a third-party website and not from the iTunes store. However, I already own this game and it's free, so this is completely legitimate. Part of my reasoning was that this version might be more interesting than the original if it was modified, but I don't do a deep enough analysis for an actual bug bounty. But this is helpful for understanding the process. So first, I'll give a brief overview of the compilation process, specifically in the context of C, C++, or Objective-C. So this begins with the source code going into the preprocessor. The preprocessor takes preprocessor directives, which begin with a pound, and replaces them with tokens the compiler will understand. For example, pound include statements are replaced with the contents of the specified files. These directives are just shortcuts which need to be expanded for the compiler. The compiler takes this code and translates it into assembly code. This is a lower level type of code and is specific to the architecture of the device. For iOS, this will be ARM assembly. The assembler takes this assembly code and translates it into machine code. The machine code files are called object files. These object files can contain references to external libraries, which will be unresolved at this point because they're in other object files the assembler doesn't know about. So finally, the object files from the assembler and all linked libraries are sent to the linker, which combines them into a final executable. Unlike the assembler, the linker is able to resolve references to the libraries in the object file. Some important definitions. So disassembler is a computer program that examines another computer program and attempts to generate assembly language source code that would, in theory, reproduce the target program. Disassembly is the code generated by a disassembler. A compiler is a computer program performing the reverse operation to that of a compiler. So in the compilation flowchart, decompiling reverses the process between the assembler and compiler, and disassembling reverses the process between the assembler and the final program. There are two algorithms for disassembling, linear sweep and recursive traversal. Linear sweep is the simpler of the two. It starts at the beginning of the code section and disassembles every instruction in order until it reaches the end. It makes no attempt to understand the control flow, for instance, branch instructions, like if-else statements or loops. Not every byte is actually an instruction or part of an instruction, so data will also get disassembled. For example, in this diagram, suppose the blue represents a branch instruction and the red represents data. Linear sweep will interpret all of these as instructions without considering what the blue instruction is. Thus, the red will get interpreted as instructions. Now, recursive traversal is the more complicated disassembling algorithm. It tries to understand the control flow of the program, detecting branch instructions and disassembling at their offsets. This generally increases the accuracy of the disassembly, but I won't get into methods of bypassing it. This is the algorithm that IDA Pro uses. As an example, in this diagram again, where blue is a branch and red is data, recursive traversal will get to the blue instruction, realize it's a branch, and then go to its offset, where it can disassembling. So the red will not get disassembled. iOS applications are written in Objective-C, Swift, C, or Objective-C++, which is Objective-C with some C++ features. These executables are compiled into ARM. Since I am focusing on reverse engineering iOS apps, I won't get into too much detail about the security architecture of iOS, but I'll mention a couple of noteworthy aspects. So apps must be code signed from a trusted authority to run on a device. Usually this is Apple, but it can also be enterprises. Enterprise certificates allow companies to have their own internal apps. Code signing goes deeper in that the device only allows pages in memory from the signed source to be executed. And as I'm sure most of you are aware, the way to get around this is through jailbreaking. Also, iOS uses sandboxing, which is more fine-grained than regular Unix permissions. Sandboxing specifies exactly what each app is allowed to access. So again, the tools for iOS reverse engineering that I'll talk about are Wireshark, collection dump decrypted, strings, NM, OTool, class dump, IDA Pro, GDB, and Cycript. Wireshark is a packet analysis tool that's able to read or write hundreds of file formats for traffic captures. While certainly not iOS specific, it is an asset in iOS reverse engineering to capture network traffic. Packet analysis is helpful for reverse engineering because it allows you to see how an app is interacting with the internet in ways that might be less obvious through static analysis. The method that I find easiest to capture traffic on an iOS device, which doesn't need to be jailbroken, is to use Wireshark with the device plugged into my computer through USB. To do this, you'll need your device's UUID, which you can get from Xcode, in the Devices window. In Terminal, use the rvictl command to create a virtual interface. This will appear in Wireshark, and you simply double-click it to begin the capture. So here's an example of some output I captured from my phone, where I opened up the game and let it play some ad on startup. The ad had nothing to do with Hello Kitty, so I don't know why Hello Kitty packets were sent. A useful feature of Wireshark is its ability to filter packets. For instance, they can be filtered by protocol. So here's an example using the same capture from the previous slide, but I filter by SSL and HTTP. Since TLS was renamed to SSL, you'll see TLS v1.2 as the protocol for some of these. I can't view the content of these packets right now because I wasn't using a self-signed certificate to decrypt the encrypted traffic. If you want to get around HTTPS, you should watch Ben's talk or Tim's talk. So the process of statically analyzing iOS apps begins by overcoming fair play encryption. iOS binaries, libraries, and plugins are encrypted but get dynamically decrypted at runtime. To get the unencrypted version requires running the binary and dumping its contents to the disk. While this can be done manually with a debugger, collection dump decrypted are more modern tools, each of which access. Since this requires shell access, these programs can only run on jailbroken iOS devices. Personally, I don't have a preference between either one. They're just both a lot better than using a debugger. Strings is a basic command line tool that outputs the strings in a binary. In this screenshot from running strings on the game, you can see an error message. You must subclass Unity www connection delegate. Though this is from the Unity game engine library, error messages are often useful for reverse engineering because they provide information about what a binary is doing in an easy-to-find format. Opening a binary in strings and piping the output through grep can more quickly and easily find suspicious behavior than having to go through a disassembler. The fifth string in this output is a format string for some kind of URL, though it isn't clear from this if it's for a local URL or a remote URL. Either way, URLs are also useful because they show how a binary is interacting with local files or the internet, which can sometimes be suspicious behavior. NM is a tool to display the symbol table of an object file. Additionally, there is a -M option for mock-O files, which displays the mock-O symbols more verbosely. So on the top here is the regular NM output, or a part of the regular NM output for that game. And on the bottom is the verbose output. So in the regular output, you see it uses single letters to identify the symbol types, so capital U, whereas the full type is in the verbose output, so undefined. Moreover, more information about a symbol is given for the verbose output, such as weak and external, and also the library where they're from, such as libc++. On OS X, there is a program called OTool, which provides information about object files. Examples of information it can provide include the header, the text section contents, the data, and the Objective-C section contents if it's a mock-O object file, and also a list of libraries the binary imports. This information is useful because it can help give an overview of certain behaviors you might expect from the application without having to deeply analyze it. It's also helpful for viewing the load commands. OTool also contains a disassembler for when you want to analyze more closely. ClassDump is an open source static analysis tool for iOS that gives Objective-C headers for iOS binaries, libraries, and it provides the same information as OTool-OV, but it's more readable and compact. So here's some ClassDump output on the left, contrasted with the OTool-OV output on the right. The ClassDump output is way more readable and looks like Objective-C, unlike the OTool output. The syntax highlighting in my editor also helped. So IdaPro is a very famous disassembler and debugger, and I know Ben talked about this in his talk. IdaPro has a ton of functionality. For instance, it is programmable through plugins. So if you're familiar with reverse engineering, you're probably familiar with IdaPro. Because it is so powerful and versatile, it is naturally an asset in iOS reversing, or any type of reversing. So I opened the game in IdaPro. I went to the strings window, and then to find interesting strings, I sorted them by their length in descending order. Longer strings have more content, which makes them possibly more interesting. A string is interesting if it indicates potential suspicious behavior. So you can see, since this is a game, it imports a lot of libraries, and most of these really long strings. A selection of these libraries are Unity, Facebook, Crashlytics, and ad networks. Some of these are also SQL database queries, which could be interesting, but after I took a closer look, I realized they really weren't. Other strings not shown here that could be interesting would be ones that look encrypted. Strings are usually only encrypted when the developers want them hidden. So when I went through the strings, I came across this start location tracking string, which caught my eye. Double-clicking the string brought me to its selector in the disassembly. In iOS development, a selector is basically a way to reference a method. Well, it seems reasonable for the app to track location for ads, for instance. I felt the name sounded suspicious, plus when I use the regular version of the app, it never asks for location permissions. The data xrefs, or data cross-references below, indicate that this is called in the start method of the IMNice class. Double-clicking on this symbol takes us to the actual method, as indicated by this __obj2_meth symbol. IDA allows you to see the cross-references to or from a symbol. Cross-references show from where a symbol is referenced, or which symbols are location, such as a method. This is important to understand the control flow of the application. There are no cross-references to this symbol, which means it isn't called from anywhere, but I can see the cross-references from it, which are the methods it calls, methods or functions. In Objective-C, methods are called by passing selectors to obj_message_send, which is seen on the right. This makes it more difficult to view which selectors are called by a method. So an example of using this function is shown here in this section of disassembly from the IMNice start method. The hard part of Objective-C reversing is following these Objective-C message send calls. To know which method is being called here and its arguments requires some ARM knowledge. Now, you might be thinking, wait, you said IDA was programmable. Couldn't you just write a plugin to improve the call graph here? Well, that's a very difficult problem, and it's definitely a pain point of using static analysis for iOS reverse engineering. To solve this problem requires knowing the register values at these function calls, at the Objective-C message send calls, which might not always be predicted from the disassembly if the disassembly is incorrect. For instance, if the binary had some form of obfuscation to trick IDA Pro. This should require dynamic analysis. Now, I did find a plugin that claimed to solve this, but the plugin, called Obviously Helper plugin, took about 6.3 hours to run on this game and made no changes. GDB is a famous command line debugger. It is much simpler than IDA Pro, but is therefore faster and easier to set up. It can be run on an iOS device directly, ideally through an SSH session, but it can also connect to debug server, allowing you to debug an iOS app remotely. So what is debug server? Well, you use debug server to establish a remote debug session connection over Wi-Fi or USB. The debug server runs on the iOS device directly. When this connection is set up, you can use GDB to connect to this server to debug the process remotely. Cycript is a dynamic analysis tool for iOS applications that provides a more readable way of modifying or viewing information about a program at runtime. The console uses JavaScript and Objective-C syntax. Unfortunately, it doesn't allow breakpoints to be used, so it can work as a debugger, but it still provides a lot of useful functionality. So some examples of basic information Cycript can provide are class information about UI components. In this last command that I ran here, I assigned one of these to a variable, so I can use it later in place of that Objective-C code. But you can do way more interesting things in Cycript. Also, worth noting is that when you're using Cycript, it is helpful to also use class dump, so you know which methods and variables exist in a class. If you try using an unrecognized selector on a class, you'll crash the app, which will then also kill Cycript, as shown here when I tried this. So iOS reverse engineering uses a wide variety of tools, and I hope now you feel inspired to go try these tools out on your own and learn more about them. So, are there any questions? So the question is, are there any tools for IPA patching? I know when I when I decrypted iOS apps manually, one part of that method was there was some bit that you had to flip in the binary, and you use that with a hex editor. But obviously that's very low level. I'm not aware of more high level tools, but it wouldn't surprise me if there were any.
Great. This has been great, Emily. Really appreciate it. And we had some fans of your memes on Twitter.
Well, thank you.